Welcome, friends of algebra. In today's video we are finally able to completely classify all the cyclic groups. So we are going to prove proposition 32, which states the following. Let G be a cyclic group with a generator X. Then there are only two possible cases, namely, if the order of X is infinite, then G is already isomorphic to the integers, or if the order of X is a finite number, a finite natural number n, then G is isomorphic to the integers mod n, C sub n or C sub nc. So those are the isomorphism types of cyclic groups, either the integers or the integers mod n. This is a very nice and strong result. Of course, cyclic groups are not that complicated, but it's the first instance where we could completely classify a certain type of group for any order, even for infinite order. The second assertion states, if G is cyclic of order n, so we have a finite cyclic group, and D is a divisor of n, a positive divisor, then there's exactly one subgroup of G of this order D. And we can also give the generator, it is x to the power of n divided by d. So we all know Lagrange's theorem, which states if I have a subgroup, then the order of this subgroup is a divisor of the order of the group. Now in the case of cyclic groups, we have the converse statement, namely if I have a divisor of the group order, then there is a subgroup of this order. And this subgroup is also unique in this case. But the converse statement of Lagrange is there is a subgroup of this order. And this, as we have seen back then, is not true in general. All right, let's take a look at the proof. And here we really apply all the things we accumulated or accomplished in the last weeks, even month. All right, we define the following map. Phi sub x, where x is the generator of G, which goes from the integers to G and maps an integer to the kth, an integer k to the kth power of x. Then this is an epimorphism. We proved a long time ago that this is indeed a homomorphism. Please pause the video and convince yourself. And clearly it is surjective because all the elements of a cyclic group look like that, x to the power of k, where k runs through all the integers. So by definition of a cyclic group, this is surjective, hence an epimorphism. This is what meant by these double arrowheads here. So if the order of x is infinite, this means by definition of this statement that there is no natural number such that x to the k is the identity. But then there is no integer besides 0 because x to the minus k is x to the k inverse. And if this is not the identity, then its inverse isn't either. So in the case of infinite order, we have only 0 lies in the kernel because only for 0 I end up with the identity. X to the power of 0 is defined to be the identity and no other integer can give me the identity here. So the kernel of phi sub x is trivial. That means that phi sub x is injective because it is already surjective. We have that it is bijective, and a bijective homomorphism is an isomorphism. So this phi sub x, in the case of infinite order of x, is the desired isomorphism between G and the integers. And here we use the characterization for any homomorphism that it is injective if and only if its kernel is trivial. So it consists only of the neutral element or the identity of this group, which in this case are the integers. Okay, now if the order is finite, n, then x to the n is the identity by definition of the order. So this n lies in the kernel, besides 0 of course. So the kernel in this case is a non-trivial subgroup of the integers. Now we use our knowledge of the integers. Every subgroup of the integers is of the form mz. For some natural number m, we actually proved that on problem set 5. So the kernel of this homomorphism is this. Now we use the wonderful fundamental homomorphism theorem, which states that this group here, mod the kernel of phi sub x, which is here z mod mz, is isomorphic to the image of phi x. This here is the fundamental homomorphism theorem, but phi sub x is surjective, so the image is all of G. So we have that here G is isomorphic to Z mod M. So the order of this group clearly is M. By this isomorphism it is also the order of G. But the order of G is the order of X because G is cyclic with generator X. And we proved in proposition 30 that the cardinality of this group here is exactly the order of the generator, and this is n. So we end up with M being n, hence G is isomorphic to Z mod n Z, and this is what we wanted to prove. So this is a very nice proof, I think, using our knowledge of homomorphisms, of surjectivity, injectivity in case of homomorphism, and of course the fundamental homomorphism theorem. Okay, now we take a look at the proof of part 2. This proof stems from my own professor that lectured the group theory course that I took at university. Peter Schmid was his name. He was a true, real algebraist. He always did neat abstract proofs, most of the time involving such group pictures here. And the idea goes as follows. We use our knowledge of the integers, especially what we said here, that every subgroup of the integers is of this form. This, of course, you need to prove, but we already did that. And then using a very general argument, we prove assertion number 2. Okay, first of all, we need the correspondence principle or the isomorphism theorem number 3. For some authors, it's number 4. So a better name would be the correspondence principle, but we need a more general form. Here is our correspondence principle, that was proposition 29. It stated that there is a one-to-one correspondence, so there's a bijective map between the subgroups of the factor group G mod n and the subgroups of G that lie above n or are n themselves. Back then we only hinted at the proof, but if you really do the proof and take a closer look at the proof, you realize there's nothing special about the canonical projection from G to G mod n. Simply the surjectivity of this map is important. So there's a generalized correspondence principle which states exactly what we need here. If we have a surjective homomorphism from one group to another group, in our proposition 29 this was pi, the canonical projection, but here it's simply an epimorphism. Then there is a one-to-one correspondence between all the subgroups here and the subgroups here that lie above the kernel of this homomorphism, or are the kernel. And we just convinced ourselves that in the case of finite order, the kernel of this homomorphism is Z mod n, because here we proved that M is n. So this is exactly the situation of the correspondence principle, but in a generalized form. So in this case, again, it states there's a one-to-one correspondence or a bijective map going from here, from all the subgroups of this group G, and in those we are interested, and the subgroups of this group here that contain the kernel, which in this case of finite order is exactly n times z. Or I think I said zn before, it should have been nz. So, and now again, we use our knowledge of the integers. What are the subgroups of Z? They are all of this form. So here I call them dz, and D must be a divisor of n. Why is that? This direction should be clear. If D is a divisor of n, then you can easily show that nz is contained in dz. You should pause the video and try that. For the other direction, if we have a subgroup, which again is of this form, that contains nz, Then in particular, n, which clearly lies here, must be an element of dz. So n is of the form d times k by definition of this subgroup, dz. Yeah, but that just means that d is a divisor of n, because n can be written as this product d times k with some integer k, and that's it. Okay, so this is the important observation about the integers. This here is not too hard, but to show that actually the subgroups are always of this kind, this required some work. We did that in problem set 5. Now, uniqueness is important in this statement. This here is unique up to the sign, because in the proof back then we showed that the subgroup is generated by the non-zero element with smallest absolute value. So you take the smallest integer, not 0, in this subgroup, and then this here generates the subgroup. But if d generates the subgroup, then also minus d generates the subgroup. But in this sense, these are unique, because if I take d or minus d, I end up with the same subgroup here, of course, because I multiply by all the integers. So we have this important statement. All the subgroups of the integers that contain this group here are uniquely determined and are of the form dz, where d is a divisor of n. So, and now we simply map those to the group G. And we use the above defined homomorphism phi sub x. So if I have a divisor of n, dc, which is nothing but the cyclic subgroup of z generated by d, corresponds uniquely to this subgroup here. And this is the generalized correspondence principle. Yeah, this is what I've written here. And phi sub x is simply the epimorphism that we use to push the integers into the group G. So we proved in proposition 31 that surjective images of cyclic groups are again cyclic, and the generator is the image of the generated d that we started with. But what is phi sub x of d? It is simply x to the d. So we arrive at the important result. If I have any subgroup of this cyclic group, it is cyclic itself, that we already know. But here we see that the generator of this subgroup is x to the power of d, where d is a divisor of n. And the index of the subgroup here is preserved under this map phi sub x. So if the index here, which is clearly d, because there are exactly d left cosets of this subgroup in Z, then the index of this subgroup here, which was generated by x to the d, is also d. Why? Because by definition the index is, or by Lagrange, the index is this cardinality divided by this cardinality. So we have the order of x divided by the order of x to the d. Now comes an important part of proposition 30, part number 4 I think it was, namely that the order of x to the d is n, the order of x, divided by the greatest common divisor of n and d. So here in this fraction I can cancel the n, and this here comes up. So I end up with the index being the greatest common divisor of n and d, but of course, since d divides n, this is simply d. This is what I meant here. So the index is conserved. So we can sum it up as follows. For every divisor d of n, there is a unique subgroup, because again, these groups here are unique, the subgroups of index d, which has exactly this index d, and it is of the form, it is cyclic with generator x to the d. Now in proposition 32 we didn't talk about the index, but we talked about the order. Here the order is not a useful concept because all the subgroups are of infinite order, so here we have to talk about the index. Here we have a finite group, so here it is better or makes more sense to talk about the order instead of the index. But we can easily switch between order and index. This is what we do here, or from index to order. If d is a divisor of n, then clearly n divided by d also is a divisor of n, because n can be written as d times n divided by d, and this here is a natural number. Okay? So, by this statement, but now applied to n divided by d, not to d, we know that there is a unique subgroup of index n divided by d, namely this here, the generator being x to the n divided by d. And if the index is n divided by d, then the order by this equation here is given by the order of g, or the cardinality of g, divided by the index of h in g. But this is this fraction here, which can be simplified to d, and this is it. So this here is the unique subgroup of this group of order d. Whew, all right. So this was not an easy proof, I would say, but in my opinion it's a very elegant proof because we use our knowledge of the integers, and then actually all is contained in this diagram if you're a group theorist. You simply have to look at this diagram and know the generalized correspondence principle, and that is it. But for a beginner, this clearly is nothing that you just take a look at and say, oh yeah, well, this is trivial. I think it's instructive to also give a second proof of statement number 2, but this video is way too long already, so we're going to make a cut here, and in next week's video I'm going to present to you a more concrete proof of assertion number 2. Alright, as always, thanks for watching, I hope you enjoyed it, and bye bye.